Alright, so hello everyone. Today's topic is partial fraction decomposition, and before looking at how to do this, let's even try to see what it's all about. Okay, so if I have this fraction 1 over x plus 1 into x plus 2, this is going to be the same as 1 over x plus 1 minus 1 over x plus 2, and you can prove it to yourself pretty easily. I mean, if you work from the right hand side, take a common denominator here, take a common denominator of x plus 1 and x plus 2, and you'll easily get your answer. Alright, so and that's what we have been doing so far. If we ever needed a fraction like this, then we take a common denominator and simplify it. However, what we'll see later is for purposes like integration and some other things, this form is pretty inconvenient. Okay, this form is pretty inconvenient, and this one is much easier to deal with. This broken down form is much easier to deal with. So and for example, this side, if you try to take the integral of this, it's pretty complicated if you just expand the denominator, but the integral of this side is pretty easy. Okay, it's if we can do it with a natural log, and also one more interesting thing is, suppose say you want to take the sum of this fraction. Okay, this fraction from say x equals 1 to n. Okay, so if you're trying to do this using this one would be pretty difficult. Okay, using this one would be pretty difficult. However, if you use this form, okay, if you use this form, then you're going to get this as the answer. And I really encourage you to try it yourself. Okay, expand, write down a few terms of this sum. Okay, and you'll see that everything cancels out except the leftmost term and the rightmost term. The first bit of the first term and the last bit of the last term. Okay, so that's pretty interesting, and we were able to work this formula out only because we broke this down into this. Okay, into this. So that's, at least I hope you can see why this process is useful. Okay, and now what we are going to try to do is develop some methods. Okay, so that in general we can break down a complicated fraction like this into smaller fractions. Alright, so that's basically partial fraction decomposition. Okay, let's see how to do this. Okay, alright, so first step is make sure that the numerator is of a lower order than the denominator. Basically, the highest power of x, or whatever the variable is, in the numerator has to be lower, strictly lower than the highest power of x in the denominator. For example, if you had let's see, x divided by x plus 1, x plus 2. Okay, this is fine. You can because here the order of the numerator is 1, right? Okay, highest power of x is 1 here, pretty evident. And here in denominator, the order of the denominator here is, well, you have x here, you have x here. These two are, the highest powers of these two factors, and if you multiply them, you get x into x, that's x squared. So the order of the denominator is going to be 2, right? It's pretty clear. So, and 2 is greater than 1, so denominator indeed has a higher order, numerator has a lower order than denominator. So this one is fine, you can move on to the next step, step 2. But however, suppose say we had x squared, okay, x squared. Now there is a problem. The numerator has an order of 2, okay, denominator also has an order of 2, okay, so that's the problem. And if that's the case, if the numerator doesn't have a lower order than the denominator, you need to do algebraic division, okay, to make it so, to make the order of the numerator lower than the denominator. All right, sorry for stuttering. Okay, so that's the first step. The second step is to factorize the denominator as much as possible, okay, as much as possible, in terms of real factors, real number factors as we can. So what I mean by that is, suppose say if you had something in the numerator, okay, something in the numerator, and you have x, okay, x to the power of 4 minus, let's see, what would be good, 64, I guess. Okay. X to the power of 4 minus 64. All right, so this is clearly, we can clearly factorize this more, right? We can definitely factorize this. So proceeding with this, you get, and this is in the a squared minus b squared form. X to the 4 is basically x squared squared, and 64 is 8 squared. So what you get is x squared minus 8, x squared plus 8, okay, and we can actually factorize this even more, okay. This one is not possible. You can only factor it if you bring in the imaginary unit, but we are not going to deal with that. But this one is again in the a squared minus b squared form. So we can further factorize this one, okay, this one. So this is going to be x minus square root of 8, and that's going to be 2 root 2, right, 2 square root of 2, but anyways, that's not important for now. X plus square root of 8, okay, and x squared plus 8, all right. And so this is as much as we can factorize denominator. This is as much as we can factorize this denominator. So, and yeah, that's what we need to do. We need to factorize it as much as possible, all right. So always need to be very about all the factors, if any of them can be factorized even more, all right. So step 3, moving on to step 3, form the partial fractions basically. So, and there are some rules for this. Each partial fraction's denominator should include only one factor, okay, which may actually I think an example would work best to illustrate this. So if I have something like x cubed, okay, x cubed divided by, let's see, 2x plus 1, oops, cubed, okay, x squared plus 2 squared, and x cubed plus 5. Right. So this is just for example. If you try to actually break this down, it's going to be pretty complicated. But this is just for illustrating this third step. Anyways, so this is, if you break this down into partial fractions, what you will get is, something like, okay, let's read through this. So each partial fraction's denominator should include only one factor, which may have a power, and also a factor is going to be repeated as many times as its power in the original fraction. Okay, and if you increase the power by 1 until you reach until you reach, suppose, say this is 3, and you'd have 3 fractions for this. Let me illustrate this. Let me not blabber on about this, just showing this is better. So the partial fractions here are going to be based on this, for these first 2 points. You'll have something like 2x plus 1, okay, and this is to the power of 1, but I don't really need to write that. Okay, and 2x plus 1, it has a power of 3, right? Here it's going to be repeated 3 times. It's going to be repeated 3 times. Squared, okay, squared plus cubed, right? So that's it. We repeated that 3 times, so that's done. But that's only for 2x plus 1, right? We need to do the same for the other factors too. And wait a second. Okay, so this is a bit unintentional, but I'm using a bad example here because this one can be factorized more. Okay, so it's something that I did not notice. Wait. Yeah, this is becoming really not neat at all. Let's see. Let me make this to the power of 4. Okay, now this cannot be factorized anymore. Okay, so now, and we need to do the same for this factor, all the factors basically. So this one has a power of 2, this one has a power of 2, so it's going to be repeated 2 times. Okay, it's going to be repeated 2 times. So we have x squared plus 2, and also x squared plus 2 squared. We increase the power, okay, as we write the other factors repeated, we increase the power by 1 every time. Saw this here too. And we have well, this only has a power of 1. It's going to be repeated only once. It's going to be written only once. So last one is x to the 4 plus 5. Okay, x to the 4 plus 5. Okay, so that's for the denominators of all the partial fractions. Okay, we've written down the denominators of all the partial fractions. There are 6 of them for this problem, and well, I didn't mention this, and the order of the numerator is indeed less than the denominator. Okay, we had to check that first. Well, I kind of subconsciously did it. Okay, it is indeed less. This is 3, right? This is 3, the order. Okay, very clearly it's 3, and this is well, you'll have an x cubed here, that's 3. You have an x to the power of 4 here, that's 3 plus 4, that's 7, and then a plus 4, so that's 11. Very clearly this is much greater. Okay, the denominator's order is much greater, so don't need to worry about that. Okay, so well, anyways, back to this. We have the last point where the numerator of each fraction is a polynomial with a degree 1 lower than the denominator's factor. Okay, the numerator is going to be a polynomial of degree 1 lower. Okay, one less power, okay, than the denominator's factor. So basically, and I'd really like to emphasize this point, the order is 1 lower than the denominator's factor, okay, for these partial fractions, not the denominator itself. What I mean by that is, okay, so this one is pretty clear. You have 2x plus 1, so this is a linear factor, first order polynomial, you could say, and so the numerator should be a 0 order, right? So that's basically a constant. So you'll have something like a, okay, you'll have something like a, And this one, you see you have 2x plus 1 squared, but what I was saying is, the numerator is going to be 1 degree lower than the factor, okay, the factor of the factor that's involved in this denominator, not the denominator itself. It's not going to be here. You won't have a first degree polynomial, okay. You'd have a 0 degree polynomial again, which is again a constant, okay, again some constant, okay. Same thing here, again some constant, because this is a linear factor, okay. And likewise this here you have a quadratic factor, right? An order of 2, so here you need to have a linear factor, an order of 1, okay, something like let's see, something like px plus q, okay, px plus q. And same thing here, you'd have a polynomial of order 1 here, so something like mx plus n, okay. And personally, a few years back I tended to get really confused about this, so I thought like, okay, so this is you have a square here, x squared plus 2 squared here, so it's not exactly this denominator as a whole, it's not exactly a quadratic. So am I supposed to put like x cubed here, or just a linear factor, a linear polynomial, or what? Okay, that's that. I really tended to get confused about that. Okay, so this, as I said, the numerator, what order it is only depends on the factor here. Okay, the factor here, not the power. The power is irrelevant. Okay, and also, well, we have this remaining. So this is a 4th degree polynomial. So we're going to have a 3rd degree here. So yeah, I'm running out of alphabets almost. So okay, so a b c. Okay, so let's use d, dx cubed plus ex squared plus fx plus g. Okay, as I said earlier, I hope you never encounter something like this. Okay, so because this is going to be really hard to solve. Okay, it's going to be a really hairy and messy problem. But anyways, this was just to illustrate the 3rd step, how we can do it in general. Anyways, so moving on to the 4th step. Multiply both sides by the denominator of the original fraction. Okay, the denominator of the original fraction, this one, and solve for the coefficients and unknowns. Basically what I mean is, so I didn't go to the other side because I'd have to scroll left and right always. But this is an equation, right? This is an equation. I set up an equation. The left hand side is equal to the right hand side. What I'm going to do is multiply both sides by this large denominator of the original fraction. Okay, if I do that, this goes out, this cancels out, and I'd only have the numerator here, which is x cubed. Now this is going to equal okay, so and you'd get a bunch of stuff here. Okay, so basically if you multiply this out, you'd get a, and 2x plus 1 cubed, you're multiplying along with the rest of the things. So one of the this 2x plus 1 would cancel out with one of the parts, so you'd have a 2x plus 1 squared, x squared plus 2 x squared plus 2 squared, x to the 4 plus 5, and you'd have same process for all the other fractions. Okay, all the other fractions, you'd have b 2x plus, okay, so let's see, this is 2x plus 1 squared, right, squared. So this and if you multiply that with 2x plus 1 cube, you'd only have a 2x plus 1. Okay, x squared plus 2 squared, x to the 4 plus 5, and the last one is c, 2x plus 1 cubed and 2x plus 1 cubed would cancel out. You only have c 2x c x squared plus 2 squared x to the 4 plus 5. So basically you do this for all the fractions basically. I think you get the idea. At the end you're going to get, the last one is going to be okay, yeah, this is going to be long to write, but anyways, you multiply all this out, and then using a few methods, there are a couple methods, we can solve for these unknowns. Okay, we can solve for these unknowns. That's basically our goal. Okay, that's basically our goal. After solving for the unknowns, we basically have decomposed our original fraction into partial fractions. Okay, we just have to substitute these unknowns into this equation. So I'll be right back. Alright, I'm back. So anyways, let's not overcomplicate stuff. Okay, so you just need to multiply it out, and then we'd find the constant. As I said before, we almost never really have to solve something this complicated. It's usually much simpler and not so overbearing on the eyes. So that's all of the steps. Okay, that's all of the steps. Now we're going to do some problems. Let's see. So the first one that I have in mind is, okay, so we have x squared plus 1 divided by x plus 5 x minus 3. All right, so this is our fraction. Okay, so the very first step is, well, make sure the numerator is of a lower order than the denominator. Let's see if it is. So the order of the numerator is 2. We have an x squared, it's the highest term, and this is x into x. We're going to have an x squared here, so order here is 2 also. So this is a problem. The numerator and denominator have the same orders. It's not lower here, so we're going to have to do some division. Okay, we're going to have to do some division. The denominator, if I expand this temporarily, it's going to be x squared. 5x minus 3x, that's plus 2x, and 5 into minus 3, that's minus 15. All right. I'd like to get something like this in the numerator also. Okay, that's one way to divide. You can also do long division if you want. You pretty much really get the same thing at the end. So let's see, x squared, we have that here. Okay, we have that here. I'd add a 2x here. Okay, I can do that, and I'd subtract a 15. All right. Okay, so that's that. And since I added a 2x, I need to subtract a 2x, right? Okay, since I subtracted a 15, okay, I need to add a 15. And you have the plus 1 remaining. Okay, you have the plus 1 remaining. All right, so that should be okay, right? That should be okay. All right, so this is what we have now. If I just want to separate this is going to cancel out, okay, with the denominator when I separate these fractions, these two fractions. Wait, so what I get is here 1, let's see, plus minus 2x plus, see, we have 15 plus 1, 16, right? 15 plus 1, 16, and x. Well, now the purpose of this expanded form, there's really no more purpose of that, so I'm going to revert to the factorized form, okay, which was given in the question. Okay, and you see that so that's step 1 done. Step 2, factorize the denominator as much as possible. Okay, now after since we did do the algebraic division, we'd have some terms here that those are not going to be involved in the partial fraction decomposition. Okay, so we leave those aside for now. Also, this is another thing that I'd like to do before doing the partial fraction decomposition, is we have common factor here, right? We have 2. Okay, we can take a factor of 2 from the numerator. So this is going to be let's see, let's actually take minus 2. Okay, minus 2. Okay, minus 2 as a factor. This is minus 2 into x minus 8 divided by x plus 5 x minus 3. Okay, and this is basically what we're going to decompose. Okay, this is the bit that we're going to decompose. Okay, so that's well, we're done with step 2. We're done with step 1. Step 3, form the partial fractions. Okay, and as I was saying, it's not going to be as complicated as previous example was. So this bit is going to be, see, we have x plus 5, linear factor, just one power, so we're not going to have to repeat it more than once, so just once. So x plus 5, and we'd have a constant on top, that's your zero order polynomial, you could say. Okay, that's a, say. Okay, so there's one partial fraction, and you'd have same thing with, for this one, you'd have x minus 3, you have a b on top. All right, so that's we have already formed our partial fractions. Step 4, we are done with step 3. Okay, step 4 is basically we need to solve for these constants. Well, before that, let's multiply out by the denominator. Okay, this big denominator on both sides. So if you do that, we get x, whoops, that was ugly. We get x minus 8 on this side, and a, so we are multiplying by, let's see, I'll just try to display this once. So we are multiplying by x plus 5, x minus 3, whoops, x minus 3. Okay, if we do that for the first fraction, x plus 5, x plus 5, those would cancel. Okay, those would cancel, and you're only going to be left with a and x minus 3. Okay, a and x minus 3. And similar for the second one, the x minus 3 is going to cancel for this one. Okay, and you're only going to be left with b to x plus 5. All right, so now we just need to find the values of a and b. There are a couple ways to do that. Okay, and when we don't have that many unknowns to solve for these partial fraction problems, it's usually convenient to just choose values of x. Okay, values of x that make the factor 0, and solve for the constants. So what I mean is, okay, x minus 3, what would make this 0? X equals 3, right? X equals 3. So if we substitute, so this is basically an identity, right? This is basically a math equation, math identity. So I can substitute any value of x I want. There is nothing stopping me from that. So let's substitute x equals 3. If we do that, the left side is going to be 3 minus 5. Okay, and this is going to be 0, right? So this is going to cancel out. It's going to be 0, and here we have b into okay, so 3 plus 5, that's 8, right? 3 plus 5 is 8. Okay, wait, why is that? Whoops, why? I was thinking, why don't I have an equation? That was really wrong of me. So this is the left side, equals 0, okay, 0, I'd even write that to not confuse myself, plus b multiplied by so you have 3 3 plus 5, that's 8, right? 3 plus 5 plus, that's 8, okay, so 8b basically. So if you solve for b, there's just b here, okay, so if we solve for it, we get b equals negative 5 by 8, okay, so that made it pretty simple to solve for b, okay, that made it pretty simple. And same thing we can do here. What would make x plus 5 0? Okay, what would make x plus 5 0? X equals minus 5, right? X equals minus 5. So substitute x equals negative 5, okay, on in this equation, and we get negative 5 negative 8, that's negative 13, equals negative 5 negative 3, that's negative 8, so negative 8a, and this is going to be 0, okay, this is going to be 0, don't need to write that. So a is going to be negative, wait, no, that's not negative, that's positive, okay, the negative signs cancel out on both sides, okay, it's positive 13 by 8, that's plus 13 by 8. All right, so we got our two unknowns, okay, we got our two unknowns, and we're really basically done. All we need to do is do all our back substitution. So what we had here is original fraction is equal to this, and we broke it up a bit more here. We factorized 2 here, and then we broke this, okay, we broke this, and what did we get here? What did we get here? So we got a by x plus 5, but a is basically 13 by 8, right? A is basically 13 by 8, so we get 13 by 8 divided by x plus 5, okay, and b by x minus 3, and b is minus 5 by 8, okay, so plus negative 5 by 8 divided by x minus 3, okay. And if we want to do some simplifications, make it look nicer, okay, this is going to be we can multiply the 2, bring the minus, etc. This is going to be, let's see, 9, yeah, so this is going to be 1, okay, and we're going to leave out whatever terms we got from we got as the quotient in the algebraic division, if we had to do that. So those we are not going to combine with the fractions, because our purpose is to break this down, break the original fraction down as much as possible, okay. So just leave those aside. This is going to be minus 2 into 13, okay, so we get minus 13 by 4 to x plus 5, okay, plus 5 by 8, right? Plus 5 by, sorry, not 5 by 8, 5 by 4, plus 5 by 4, okay, plus 5 by 4, x minus 3, right? X minus 3, okay. So voila, we broke down this large fraction into this much simpler form, okay, this much simpler form. And if you ever had an integration problem, if you ever had to integrate something like this, that would drive anyone crazy if they try to do this by brute force. But this is much simpler, okay, you can integrate it directly. It's just one line away from your answer, okay. So that's done. Let's move on to the next problem. And well, before that you might have noticed this method that I used here, just when we have linear factors like this, and we could just make these factors 0. Okay, we made these factors individually 0. We found the constants. This method can be simplified. Okay, this method, you could say we can do it in a shorter time. Okay, that you could say it's a shortcut, and the way to do that is, by the way, the proof of this method that I'm going to show you, this shortcut, if you want to see it, please do stick until the end of the video. Okay, make sure to do so. And let's see how to, let's look at another problem, and I'll show you the shortcut there. Actually let's do it with this one. Okay, let's do it with this one, just to see that our method works. Okay, just to see that our method works. So we broke down x minus 8 divided by x plus 5, x minus 3. Okay, so and this would be equal to x plus 5 plus x. Okay, so something divided by x plus 5 plus something divided by x minus 3. And the way to use this shortcut is, okay, pretend that, okay, for if we want to find the constant for x plus 5, the numerator for this one, okay, pretend that x plus 5 here, okay, on the left hand side, doesn't exist. Okay, whoops. Okay, well, first thing, what makes this 0? Okay, what makes this 0? Well, x equals minus 5. Okay, now pretend that this does not exist. Okay, pretend that this does not exist, and evaluate this fraction. Okay, so if I do that, I'd get minus 5 minus 8, that's minus 13, divided by this. There's nothing here. Okay, it doesn't exist. When I do this on paper, I cover up the fraction with my finger. Okay, divided by negative 5, negative 3, that's negative 8. So let's see, we have my, oops, not here. Okay, so we have minus, let's see, minus 13. Okay, minus 13 divided by minus 5 minus 3, that's minus 8. It's minus 8. This is 13 by 8, right? 13 by 8. And that's basically going to be your numerator here. That's basically going to be your numerator here. Okay, pretty neat, right? Let's check. Did we get the same answer here? We did. We did. This was the numerator, the constant for x plus 5. Okay, let's try to do it with x minus 3 also. So can I take this back? I don't want to pretend that this doesn't exist anymore. Let's do it here. So for the next one, let's pretend x minus 3 doesn't exist. Well, first thing, what makes this 0? X equals 3, right? X equals 3. So now this doesn't exist. Okay, we're pretending that doesn't exist, and evaluate this fraction at x equals 3. Okay, x equals 3. So we get 3 minus 8, that's minus 5, divided by 3 plus 5, that's 8. So minus 5 by 8, minus 5 by 8, minus 5 by 8, which is what we got here, Pretty neat, right? So this makes it really easy to find these constants, but this shortcut does have its limitations. Okay, I at least need to mention that, and I'm going to show you what are the implications of these limitations in a bit. But okay, so if I just needed to word that, you can only find the constants. Okay, the constants for the linear factors. Okay, the linear factors of, wait, how do I word this? I'm just coming back in. Alright, I'm back. So I guess the neat way to say this is, you can only find the constants for the highest powers of each linear factor. Okay, the highest powers of each linear factor. I'm going to show you what I mean by that in a bit. Let's see for this one. Suppose say x, we had x plus 5 and x minus 3. This has a power of 1. This x plus 5 factor only has a power of 1. Okay, and we only get x plus 5 here. Okay, just one. It's just written once. That's why we can easily find the constant for this one. Same as this, there's nothing about repetition here, but when there is repetition, we can only find the constant for the highest power of each factor. Okay, the highest power of each factor. I'm just going to, okay, so it's better to illustrate this by an example. And I have another one here. Let's do x squared plus 2, divided by x plus 2 squared, and x plus 3. Okay, so this is going to be some constant. Well, I don't know exactly what what went on when my my battery died. I don't know. Did an delay enter this video, or well, I need to check that. I'm sorry for the interruption. So my battery died basically. So should have put it on charge before recording this video. Just forgot about that. Anyways, so we have some constant actually over x plus 2. Okay, so for this factor we need to repeat this twice. Okay, we need to repeat this. Also we have, whoops, not one. Why am I writing one? So it's going to be some constant here divided by x plus 2 squared, and we also have that x plus 3 factor, right? X plus 3 factor, so some constant over x plus 3. Now what I was saying is okay, so we have x plus 2 and also x plus 2 squared. This factor had to be repeated twice, and using this shortcut you can actually find only the value of this one. Okay, the constant here. Okay, you cannot find the one here. Okay, this one for the x plus 2 factor, this one has the highest power, right? This one has the highest power, so you can only find the value for this constant. Okay, all right, but however that doesn't mean you cannot find this one, because this is a different factor. Okay, as I said before, it's for the highest highest power of each factor. Okay, each type of each factor. So this is a different factor from that one. You can find the value for this using the shortcut. You can find the value for this, but not the value for this. Okay, so but still it's two factors, 2 out of 3 done if we are able to use the shortcut. So let's jump right into it. And first thing that we needed to check is that the numerator does have a lower degree. This is 2. Be right back. Alright, so as I was saying, what makes this 0? This one. So it's x equals -2, right? -2. Oh yeah, wait, yeah, so kind of lost track. What I was saying is, so this is degree, degree of 2. The denominator is 2 and 1, so it's a third degree polynomial. So yes, indeed, numerator is has a lower degree. Also, this is as factorized as it can possibly get. Cannot factorize it anymore. So let's see, we're done with the first and second steps, right? So yeah, now forming the partial fractions. I kind of jumped to that, shouldn't have done that. So all right, shortcut. So x equals -2 makes this 0. Now pretend that it's not here, okay, and evaluate this, okay, at x equals -2. Let's do that using the calculator. So I have let's see, -2 squared, same as 2 squared, or 4, plus 2 divided by -2 plus 3. Yeah, -2 plus 3. Yeah, okay. So that gives me 6, right? That gives me 6. So, and this is going to be the, let me remove that. Okay, this is going to be here, okay, 6. And for this one, let's say, well, this is 0. This is 0 at x equals -3, right? -3. Okay, and let's pretend that it's not there. Let's pretend it's not there. So evaluate this fraction at x equals -3. Okay, so we have -3 squared, or 3 squared. That's basically 9. 2, 2, and we have -3 plus 2 squared, right? Yeah, -3 plus 2 squared. That's 11. That's plus 11. Okay, that's basically going to be here. Okay, it's basically going to be here. So we've already found 2 out of the 3 constants that we need to find. Okay, let's say that third one, say this one is a. Okay, and how should we go about finding this? Well, we could wait, should have removed this line. Okay, anyway, so the x plus 3 is here now. Okay, it is here. Okay, so as I was saying, we could multiply both sides by this whole thing, but I think it would be much easier if we just set x equals 0 as it is. Okay, just substitute x equals 0. It wouldn't make the denominator here 0. There's really no problem with that, and kind of seems like the most efficient way to do this. There's really quite a bit of flexibility with finding the unknowns most of the time, so there's no need to worry about stick to one particular method all the time. So if I set x equals 0 in this equation, what I get is 2 divided by, well, 2 squared plus 3. Okay, that's 12. Okay, 2 by 12, or that's 1 by 6 basically. Here I have a by 2. Okay, here I have 6 by 2, which is 3, and here I have 11 by 3, right? Yeah, 11 by 3. All right, so this should give us, let's see, 1 by 6. Oops, not 6. It's freezing. 1 by 6. Okay, 1 by 6 minus 3 minus 11 over 3, and yeah, okay, so first this, then was this executed correctly? all right, multiply by 2, that gives me minus 13. Let me just check once if this is correct. That's this one is good, this one looks good. If I set this to 0, we have 2 here, 2 squared here, that cancel out. 1 by 6, yeah, okay, this 6, oh yeah, okay, my bad. So what happened here is this got covered, here. Okay, I couldn't see the power there. It's 6 by x plus 2 squared, okay, 6 by x plus 2 squared. This should have been 6 by 2 squared, 6 by 4, okay, 4. So instead of 3 here, you have 6 by 4, or 3 by 2 here, okay, 3 by 2. Now I think we should get the correct answer. 1 by 6 minus 3 over 2 minus 11 over 3 equals minus 5. We multiply by 2, that gives us minus 10. Okay, so a is minus 10. Alright, so that gives me my last constant. So this, we can just put minus 10 here. Voila, we have broken this down into partial fractions. The shortcut wasn't enough to do the whole thing, but it got us 2/3 of the way there, and just by substituting x equals 0 into what was the equation that we got, we were able to solve for a, and that's done. Okay, that's done. Now I'd like to do some, these are mainly the things you encounter most of the time. If you have some integral or something else, most of the time it's some linear factors, maybe one quadratic, and yeah, that's what I was saying. I want to focus on some harder problems now. So let's try our hands at some harder problems. Okay. Let's try to master this topic. So the next problem I have is, let's see, yeah, this one is definitely up there with the hardest one. So x squared divided by 2x plus 1 squared, 2x plus 1 squared, and x squared plus 6, okay. So step 1, so this is this is degree 2, this is 2 plus 2 is 4, this is degree 4. Yeah, first step check, don't need to divide. Second step is, well, this needs to be, denominator needs to be as factorized as possible. This one is, and this one is 2. You cannot actually factorize it anymore, at least if you don't bring the imaginary unit in, which we are not going to. Within real numbers, this is as factorized as it can get. Alright, so step 2 done. Now we just need to break this into partial fractions, and to do that, let's see, sum constant a by 2x plus 1. Need to repeat that. 2x plus 1 squared. Okay, but as I said, this is this is a linear factor. And this is the highest power for this factor, right? This linear factor. So we can actually use a shortcut to find the value for this one. Okay, let's first do that. So to do that, here we'll pretend. Okay, so first thing, what makes this 0? X equals minus half, right? X equals minus half. Okay, now pretend it's not there. So evaluate this fraction at x equals minus half. So I have okay, this is really freezing bad. Okay, so what I have in the numerator is minus half squared, that's 1 by 4. Okay, and here okay, so again 1 by 4 plus 6, so 6 plus 1 by 4, right? Yes, everything looks good here. Okay, 1 by 4, 6 plus 1 by 4, and I get 1 by 25. I get 1 by 25. Okay, so 1 by 25. All right, and we're not done. There's another fraction here, which is x squared plus 6. Now this is a quadratic 2-degree polynomial, so we need a 1 degree in the numerator, so that's going to be, let's say that's bx plus c. Okay, so now we just need to solve for a, b, and c. Or step 3 is done. Now we just need to solve for a, b, c. To do that, let's multiply both sides by this thing, and what we get is x squared equals a 2x plus 1 x squared plus 6 all right, plus 1 by 25. Let's see, so that fully cancels and we get only x squared plus 6, and lastly we get bx plus c multiplied by 2x plus 1 squared, right? Okay, all right. Okay, so this is our equation. Now we just need to find the values of a, b, and c. Let's see how to go about that. So x cubed here we have, and x cubed here too we have, constant here. Okay, we have an x squared here, and okay, so as you can see, one thing we can do, we can substitute some values of x, okay, and make some simultaneous equations, okay, to solve for the and then solve for the unknowns. Let's try to do that. And we could also do something like this. This is the second approach that I'd like to show you. This is quite useful. Sometimes you know, it just gives the unknowns pretty easily. So let's see that too. And this is basically equating the corresponding coefficients on both sides. Okay, so what I mean is, here on the left hand side, suppose if I wanna equate the coefficients of x cubed, okay, on both sides. On the left hand side there is no x cubed term, so the coefficient of that is 0. On the right hand side, I'll get an x cubed here. I'll get a 2x cubed here, okay, that's the highest term, and I get an a here. So the coefficient, okay, x cubed here is 2a, okay, but we are not done. This one has no x cubed in it. This one does have, okay, so this is we'll get 4x squared here, and then you multiply by bx, so you get 4bx squared, okay, so plus 4b. Okay, so this is basically what happen, you know, what we get when we equate coefficients of x cubed. Okay, so that gives us one equation. Okay, so let's try to figure out another equation. Let's equate the coefficients of x squared. Okay, let's equate the coefficients of x squared, and what we'd get is, like, so it's 1 here, left hand side is 1x squared, and here we get x squared here, and that seems to be the only one. Okay, so we get a here, Okay, we get 1 by 25 plus 1 by 25. Okay, and we here what we'd have is, okay, you know what, let's expand this a bit. Let's expand this. So this here, whoops, this would be 4x squared plus 4x plus 1. Again, the x squared coefficient here would be, well, 4b, okay, bx into 4x, that's 4b x squared, 4b. So, and also let's see, c, yeah, 4cx squared, so 4b plus 4c, basically 4b plus 4c plus 4b plus 4c. All right, so that's another equation. Well, we can simplify this a bit, you know, subtract 1 by 25 from both sides. Here you'd get 24 over 25, 24 over 25. Okay, that's another equation. And whoops, not one, so second equation. And well, as I said, doesn't mean that we need to stick to the same method over and over again. Let's try the thing that we did before. Let's set, let's plug in some value here, and here you cannot, you can, suppose say plug in x equals minus half here to make this 0. Okay, make this 0. Like what we did before, but you'd see that if you use the shortcut as much as you can, before coming to this, equating anything to 0 wouldn't actually bring any benefit to you. Okay, so it's not going to solve anything. Okay, so that's a dead end right there. So instead we'd need to substitute other values, suppose like x equals 0. Okay, it's the easiest, obviously. So if I do that, I get 0 on the left hand side equals, so let's see, 1 into 6a. I get 6 by 25 plus 6 by 25, 6 by 25 here, and I get, so b into c, that cancels out, so c, just c here, and just 1 here, so plus c, yeah, plus c, and that should give us that. If I just simplify this a bit, I get 6a plus c equals minus 6 by 25. This is our third equation. Okay, so this was our second equation. Okay, so all we need to do is solve these three simultaneous equations. Okay, let's try to do that, and we'll definitely use the calculator for this. You can do it by hand, it's just going to take a while, and it's not exactly the purpose of this video. Let's see, we have three unknowns. Okay, 2, 4, 0, and 0 on that side. Okay, 1, 4, 24 over 25, right? Yeah. Okay. Lastly, 6, 0, coefficient of b is 0 on the third equation. C, that's 1, and negative 6 over 25, oops, not 5, 25. Okay, so this gives us a equals minus 48 by 625. Okay, I kind of already knew that these answers wouldn't be pretty, but well, in real life, it's not like you're going to get all unknowns being integers or something like that. So anyways, a equals negative 48 by, what was it, 625? Yeah, 625. Okay, b equals, let's see, 24 by 625, and c equals 138 by 625. All right, so and substitute, we got our values, we got our unknowns, and substituting them here, where is it, here, okay, we see that this, and simplifying a bit, see that this, if we break this down into partial fractions, would be minus 48 625 2x plus 1. Okay, then we have 1 over 25 2x plus 1 squared. Then we have last but not least, I'll make a partition here. Let's see, 24x plus 138 divided by 625 x squared plus 6. Okay, so that's this thing broken down to partial fractions. It was a bit difficult, but I'm pretty sure it's it's quite satisfying. Okay, bringing this thing down. All right, so let's try one more difficult example per se. Okay, let's see. And this one there's actually quite a bit to learn here. There's quite a, and it's pretty interesting. This is x to the power 4 divided by x plus 1 x cubed plus 1 All right, so again we just need to complete our 4 steps. That's all that we need to do. Step 1, make sure the numerator is of lower order. Okay, so is it let's see, this is order 4, this is x into x cubed, that's also 4, so it's not. We are going to need to divide. So here the denominator is going to be let's see, x to the 4 x cubed is here plus x cubed. Okay, there's no x squared term. Okay, plus x, there's only one x term, and plus 1. All right, that's our denominator. Numerator, we could do long division to simplify this, or we could do this too. Let's see, we have x to the power 4, that's already there. Let's add an x cubed, add an x, and add 1. All right, but we cannot just add things as we want. We need to subtract the things that we are added also. So I'm going to subtract x cubed, x, and 1. All right, so if we do that, we're going to get so this cancel out if we separate the fractions. So this is 1 minus x squared plus x, not x squared, sorry, x cubed plus x plus 1. Okay, x cubed plus x plus 1, and we don't need this expanded form anymore. We can revert back to this, and there's the second catch we have here. Wait, actually I'll write this down for now. I'll write this down. Sorry, not x cubed plus 1. Okay, so that's our first step done. Next, factorize the denominator as much as possible. Okay, now if you're not careful with this, it might appear that the denominator is factored as much as possible, but actually it's not. If you have studied this in school, you might remember that x cubed plus some constant or minus some constant, that can actually always be factored. we have x cubed plus a cubed. We can factor that. It's going to be x plus a multiplied by x squared minus ax plus a squared. Okay, I hope I got that right. So we're just going to use that here. Okay, this we're just going to use that here. So if well, basically here the a is 1. Okay, the a is 1. So this is going to be, this thing is going to be x plus 1. So x cubed plus 1 is going to be x plus 1 x squared minus x plus 1, and well, we're just going to substitute that in here, and there is also an x plus 1 here to go along with what's already here. So if I simplify this, this is going to equal, oops, forgot about the one. Oh, wait, sorry, no. Okay. Forgot about the one there. So this is x cubed, right? Yeah, x cubed plus x plus 1, and denominator we're gonna have x plus 1 and into x plus 1. That's x plus 1 squared. Also x squared minus x plus 1, x squared minus x plus 1. Okay, so that now it's as factored and simplified as possible. You can check it out yourself, but you'd never be actually be able to factor this using real factors. Okay, you need to bring the imaginary unit. In general, when you use this formula, this quadratic bit cannot be factored in terms of real factors. All right, so step 2 is done. Now we just need to form our partial fractions, right? Form our partial fractions. So, and for that we are going to ignore that 1 right there. We're going to ignore this and also ignore the minus. So we're just going to work with this. So just that part is going to equal, so something over x plus 1, some constant over x plus 1, okay, plus some other constant over x plus 1 squared. This is squared, so that's why we're going to repeat this, okay, 2 times. Okay, and well, we can actually use our shortcut here. Okay, linear factor has power here for that one. So well, so this is 0 when x is equal to minus 1. Okay, we're gonna pretend it's not there. And evaluate this fraction at x equals minus 1. Evaluate it at x equals minus 1. Let's see. If we do that, minus 1 and plus 1, so that's minus 1. Divided by, let's see, 1 plus 1 plus 1, so that's 3, right? Yeah. 1 plus 1 plus 1, so let's see. I didn't need the calculator actually, so that's just minus 1 by 3, right? Just minus 1 by 3. Okay, so that's minus 1 by 3. Okay, that one is done, and we have another one. This is x squared minus x plus 1. This is a quadratic, right? So we need a linear 1 degree term here. So this is, let's say, no, not a again. We'll say that this is bx plus c. Okay, we'll say this is bx plus c, and I think you get the idea. Okay, you'd again need to, as we did before, multiply out well, this is, I always forget to remove that line there. What makes a good contrast? Yellow. Okay, yellow over this. So this is now definitely there. Okay, cannot ignore that. So what we need to do is multiply out both. So just this part is equal to this. Okay, just this part is equal to that. We then need to multiply out both sides with this, okay, the denominator, and then just solve for our three constants. I'd really encourage you to do it yourself, okay. That would make for really good practice. And what you get at the end is a is gonna equal 1, okay. B is gonna equal let's see, B is gonna equal let's see, B disappears, so that's 0, okay. That's good. And C is gonna equal 1 by 3. C is gonna equal 1 by 3. Okay, so substituting these values in here, okay, what we get is our original fraction, this one, where is it? This one becomes 1, okay, 1 minus 1 over x plus 1. Well, this is just this was just a word of caution. This is some sort of mistake I often make, but after substituting all these values here, please don't forget that you have a negative sign here, okay. Do not forget that. That's a sort of mistake that I make a lot. So that's just a word of caution. So this is again 1 over 3 divided by x plus 1 squared, and we have negative 1 over 3 x squared plus x minus x plus 1 minus x plus 1. Alright, so I think this was a pretty good, pretty interesting example. We saw a couple of things. Well, first thing, we had to do the division, and we also saw that why we need to be wary of step 2. Okay, usually especially when you have the denominator factored to a certain extent, we let our guard down, but it might not be factored fully, as we saw here. Okay, so you'd always need to factor it as much as possible before doing these partial fractions. Okay, otherwise things would become really complicated. That's not really the correct method either. Okay, so that example is done. So that's all for our hard examples. Last thing I want to discuss, hope it doesn't take too long, is sometimes you can do substitutions for your partial fractions before doing partial fractions. That can sometimes make things easier, and in very special cases actually. Let me show by example. So let's say we have x squared, 6 over x squared plus 2, and x squared plus 4, right? So, and as you can see, well, numerator is definitely fine, less order than denominator, and these cannot be factored anymore. So step 1 and step 2, we're good with those. Now you need, you might think, okay, so at first glance, so we need to, if we are going to form the partial fractions, would be something like this, right? Ax plus b, x squared plus 2, and because this is a quadratic, we need a 1 degree polynomial here, cx plus d, x squared plus 4. Okay, so this should be our normal procedure. It's definitely going to take a long time, and for this special case, I'm going to discuss what are the kind of criteria, although you no need to memorize them or anything. But this special case, we can actually make a substitution to make our life much easier. If you see here, if you see this fraction, you have an x squared here, you have an x squared here. Let's try making the substitution u equals x squared. Okay, let's just try that. Okay, so if we do that, what does this become? This becomes 6 over u plus 2 u plus 4. And what do we have here? Here we have a fraction where we only have our 1 degree terms, right? Our 1 degree terms. All the this is much simpler than that one. This is much simpler than that one. If we want to break this down into partial fractions, that's way easier. We can even use a shortcut here. So we can even use a shortcut. For one thing, what would make this 0? U equals minus 2. U equals minus 2. Pretend it's not there. Pretend it's not there. So then evaluate this at that value. So the 6 by minus 2 plus 4, that's 2. So that's 3. That is 3. So this would be 3. This would be 3 divided by u plus 2. And this is gonna be u plus 4. Similarly, this would be 0 at, again using a shortcut, this is 0 at u equals minus 4. Pretend it's not there. 6 divided by minus 4 plus 2 is minus 2. 6 divided by minus 2 is minus 3. So the numerator is minus 3. Okay, so we broke that down into partial fractions pretty easily. Now all we need to do is, this was our original fraction, that's our target, breaking this down. Okay, so all we need to do is do the back substitution. We have do the back substitution, okay, in this equation. So we have x squared plus 2 x squared plus 4. Okay, I'm just back substituting for you. So this is going to equal 3 over x squared plus 2, that's u, and minus 3 over x squared plus 4. Voila, we have our partial fractions. So we got them pretty easily, right? We got them pretty easily. So substitution made our life much easier, and I'd encourage you to actually try this out. Okay, try this out in your normal way. You'd see that A and C would disappear. You'd get the same answer, but it's more than apparent that this is much easier. If you make the substitution here, if you just cast that, this becomes much easier. Let's do another example. Suppose, say we have x to the power 6 divided by 3x cubed minus 1, okay, and x cubed plus 4. Okay, so this one is a bit more complicated, but you might notice certain things. So we have x cubed here. Don't exactly have that here, but well, x to the power 6, this is just x cubed squared, right? X cubed squared. So let's make the substitution u equals x cubed. So this becomes u squared divided by 3u minus 1 u plus 4. Wow, this has become much simpler. If you try to do this in a normal way, the first thing, you'd need to divide it algebraically here too. But anyways, I think you can imagine, it's a third degree, these are, three degree factors, okay, and the numerators for those are quadratics, and solving for those is it's really a headache. Okay, it's going to be migraine inducing. All right, so definitely not going to go through that if we can avoid it. So this is much simpler. We just need to okay, first thing we need to algebraic. Okay, so this is still a degree of 2, and this is a degree of 2 also. So first thing we need to divide it. So let's see. Actually, well, I'm not going to waste your time with all of that. We have done these examples before, right? The first one was exactly something like this. So let's see. The answer is going to be for this one. Saves us the time, and basically we know how to do this, right? We know how to do this. Where did it go? Hey. Okay, so just want to see how substitution is useful here. That's my goal here. So if I break this down, this one into partial fractions, this is going to be 1 by 3. Okay, and this is what we get, after divide, the quotient of the algebraic division. So that with that done, the other two numerators here, this is, we are going to have 3u minus 1, 3u minus 1, and u plus 4. We can use our shortcut, and if you do that, we get the numbers 1 by 39 here, 1 by 39 here, and we get minus 16 over 3 here, minus 16, oops, sorry, minus 16 over 3 here, not 3, sorry, 13, minus 16 over 13 here, 1 by 39 here. And finally, this was our goal, right? This was our original fraction. This was in terms of x, not u. So we need to back substitute. We need to back substitute this. So what we get is 1 over 3, 1 over 3. Okay, so this is seemingly very complicated partial fraction. Normally, if there's something like x cubed and x to the 6, I'm going to be petrified and not try to do that problem. Okay, if I had to do it the long way at all. So, but thankfully we didn't have to do that. This was much simpler due to substitution, and thus we get let's see, so 16. Hey, I didn't bring the 39 down. Okay, it doesn't really matter, but anyway, so just a bit of beautifying, you could say. Cx cubed plus 4. Voila, we have our answer. This was much easier than what it might have looked like if we didn't know the grandness of substitution for this one. Okay, so that's it. We saw how substitution was useful, and if you're curious, the in general problems that would be simplified by substitution, this is the criteria. So you'd have something like some polynomial p to the p of x numerator, and I'll assume that you have already done the division if you had to. Okay, if the numerator had to be broken down a bit. So, and in the denominator you have let's see, some factors like, let's see, a x to the n plus b. Okay, let's see, c x to the same n plus d. Okay, so the thing is, if you can write this equivalently as some, this is basically targeting the numerator. If you can write this equivalently as some function, some polynomial. Okay, so not just any function, some polynomial. I'll show that why it's important in a bit. Some polynomial q of x to the n. Okay, and a x to the n plus b. If you can write it like this, where everything, all the terms are some polynomial, every factor here, the numerator here, all of them are some polynomial of x to the n, of x to the n, then the substitution u equals x to the n will be really helpful if you do that. Then the substitution u equals x to the n would be really helpful, because then it would just simplify to some polynomial q of u, okay, divided by a u plus b plus c u plus d. And I'm not saying the denominators need to be something like this. You could have a square here, you could have a cube here, you could have some d, if you had something like this, like d x to the 2n plus e x to the n plus f, okay, something like that even. Okay, that would also be, that's also a polynomial in x to the power n, right? That's also a polynomial in x to the power n. If you make the substitution, you'd have something like du squared plus eu plus f. Basically what I'm saying is, if everything, every factor, every term is a polynomial in x to the power n, okay, then you should make the substitution e equals x to the power n. That would make your life much easier. All right. And why is this required? Suppose, say, if I just made a small modification here, if I just made a small modification here, okay, suppose that this was, wait, where did my example go? If I just had instead of 6, some 6x here. So after making, if I went ahead and made the substitution, 6x is definitely not a polynomial in x squared. And substitution, what it does is, here you'd have u to the power of half, okay, u to the power of half, and this is not a polynomial, right? This is not a polynomial, and partial fractions, partial fractions, you need polynomials. Every term has to be a polynomial. So you cannot proceed any further, and it has become something weird. All right. So that's why you need that requirement. Most of the time, it's we don't really need to memorize. This is something that you just notice and make the substitution, okay, to make your life much easier. So that's it for that substitution. And well, this is really most of the video. All the techniques that I have to show, I've already shown. The rest of it is the proof for the shortcut that I showed before, the proof for this shortcut, this one, okay. And also, I'd like to recommend a good website. It's not some promotion or anything, but there's a good website. You can do partial fractions and some pretty other interesting thing. I find it's useful for my homework and stuff. But anyways, let's move on. So the first thing is the proof. Okay. I'm going to be a bit general with this, okay. I'm going to be a bit general. So let's say we have polynomial p of x here and some linear factor ax plus b. Okay, let me use some different letters. Okay, so let's say we have mx plus n. Okay, to some power k, okay, to some integer power, positive integer power k, and some, the rest of it can be some, q of x, okay, product of some other factors. Doesn't matter what they are. So what we can do, if we break this into partial fractions, I'm assuming p has a lower order than this, okay, and this the denominator. Anyways, if we break this down into partial fractions, what we get is, let's see, we have some constant, okay, say it's a1, okay, divided by mx plus n plus some constant a2 divided by mx plus n squared. And this is going to go on until we reach the kth term for this one. So this is a sub k, okay, divided by mx plus n to the power of k, right? Okay, and there's, well, we have the q of x, and there's going to be something in the top. So that doesn't really matter, as we'll see. So this is the breaking this down into partial fractions. Let's see. Now let's multiply both sides by just mx plus n to the power k, okay, just this, okay. Let's multiply both sides by that. So we have p of x divided by, this is just q of x remaining, okay, q of x remaining. This is going to equal, no, wait, a1, and well, we have mx plus n to the power k multiplied here, and we have divided by mx plus n, so we have mx plus n to the power k minus 1 plus a2. I think you get, I think you get the trend here. You get mx plus n to the power k minus 2 all the way up to wait, just for view's sake, I just for the sake of making this easier to see, I'll write it here. This is the main thing, actually. This is the main term here. So this is mx plus n to the power, okay, wait, no. Well, it wouldn't be incorrect to write power to the power 0. That's just redundant, because as you can see, if we multiply by mx plus n to the power of k, this just cancels out. We just get a sub k here, okay? And then we have something like, let's see, something over q of x, and we have mx plus n to the power of k, right? Now let's substitute. Let's see what makes mx plus n 0. Okay, what makes mx plus n 0? Well, we can just solve for it. So that x equals negative n by m. Okay, so basically this makes mx plus n 0, right? This makes mx plus n 0. Let's substitute that x, okay, in this equation. Let's substitute that in this equation that we got. If we do that, on the left hand side we get p of that particular x, okay, n by m divided by q of negative n by m. Okay, so this is going to equal, so this is, well, this power is not going to be 0, until we reach this, the powers are not going to be 0. All right, so this is some power, and this is 0 to the to some power, some positive power. So this is 0, this is 0. As you can see, all of these are going to be 0. Okay, all of these are going to be 0. You're going to be left with this, and this is also going to be 0. So this is also going to be 0. This whole thing goes out. So all that we have left on the right hand side is a sub k. Voila, this is our proof. Basically what this is saying is your the constant a sub k, which is the numerator for mx plus n to the power k. This is the fraction with the highest power for mx plus n. Okay, the highest power for mx plus n. The numerator of that, the constant for that, is just going to be this. Okay, and what is this basically? This is what you get when you go back to the original fraction. This is what you get if you ignore this part and just substitute the value of x that makes this 0 into this fraction. Okay, into this fraction, right? So then if you do that, you'd get this, right? You'd get this. So that's my proof. That's our proof. All right, and last but not least, what I want to show is symbol love, actually. So as you can see, I find this really useful. Like sometimes when I do some heavy integral problems, I'm not really always keen to check my do my partial fractions by hand, and sometimes I just want the answer for some things like perfect squares, etc., and maybe even check my homework. That's also possible. So all that I can do it pretty easily if I just enter my problem here. Let's actually try entering one that we saw before. See that we got it right, actually. Let's see. So x squared plus 1 divided by x plus 5 into x minus 3. Let's see if that gives us a reasonable answer. So x squared, wait, I need a bracket here, right? Yeah, so x squared plus 1 divided by x plus 5, right? So x minus 3. All right, so if I just proceed with this, voila, seems like, yeah, our answer was right. So this was my answer, right? Yeah. Let's see. Yeah, this our answer does match. So as you can see, it's pretty easy to get the answer here, and well, they have even showed this. Well, have they? Oh no. Okay. Whoops. Okay. So no, but at least it gives the answer, and I find it pretty useful for when I'm just trying to use this thing, okay, rather than showing all the steps. And you can do the same thing with Wolfram Alpha, but the computation times a bit slow for individual items, and this is pretty fast, right? This is pretty fast. I got this answer pretty quickly. Anyways, this is not some promotion or something else. I just found it pretty useful for some basic stuff like inequalities and performance of complete squares, etc. So just wanted to show you two guys. Anyways, that's the end of the video. This is pretty long, and I'll see you guys in the next lecture. Please do leave any suggestions you have in the comments, and if you like this video, please leave a like, please subscribe, and support this channel in any way you can. Okay, and also well, okay, if was I gonna say anything else? No, that should be more than enough. That should be more than enough. Okay, if you do find some discrepancies or errors in this video, yeah, please do point them out. Okay, I'd be more than happy to correct them. All right, so that's the end.